farms. I'm going to briefly introduce the main objectives and the hypothesis. Afterwards, I will briefly describe the selection process that I've used to find what we believe is an optimal topology for this application. The topology is entitled the SRC sharp, stands for series resonant converter sharp, and I will go into more details about the topology. Afterwards, I will discuss about the medium voltage experiments which were performed here at the university, and finally conclude. And during the presentation, you will basically observe two storylines. One is focusing on the academic research, on the scientific methodology, and the other one is focusing on the engineering challenges, because there were many practical challenges that had to be encountered. So, 3.5 years ago, we basically started with a simple question: how can we decrease the cost of technology for wind farms, and especially for offshore wind farms that are employing HVDC transmission? One could say a case could be made for MVDC collection network. So if we can transition from NVAC on the collection grid, on the turbines, to MVDC, we could actually decrease the cost of technology. So, for instance, looking at a comparison of today's present solution, where we have 66 kilovolt AC on the collection network, the future solution is going to require turbines with medium voltage DC output. It's going to require DC cables and all the necessary switchgear. Plus, it's going to require MV to HV substation converter. And my main focus was on the turbine converter. And based on previous studies, which evaluated the annual energy losses, if we should compare the 66 kilovolt AC wind farm with the plus minus 50 kilovolt DC wind farm, we should expect 1 to 2% savings on losses, 1 to 2% savings on bill of material cost. The problem is that there are no commercial DC-DC converters, there are no standards, there is no experience, and this is where hopefully my work is going to fill some gap. So, in very simple terms, my objective, as I said, was to focus on the turbine converter, and it was to identify an optimal circuit, and the specification that we had in mind, they range from 5 to 15 megawatts. Input voltage 0.5 to plus minus 8 kilovolt DC, while on output between plus minus 35 to plus minus 50 kilovolt. Switching frequency in the level of kilohertz, so we're talking about very tough specification. But we also decided to make some design freeze, so we had some requirements like the converter must be unidirectional, should have confining separation, the transformer must be designed for high voltage gain, and very importantly, it should employ off-the-shelf technology. Of course, one could talk about different wind farms configuration, and here on the left side we can see today's solution, NVAC and HVDC for transmission, or NVAC plus HVDC for transmission. The wind farm configuration that we envision is a simple two-step configuration where the turbine is increasing the voltage to MVDC, and the offshore substation converter is further going to increase it to HVDC level. Of course, one could also talk about having MVDC at the transmission level, but I'm not going to go into detail with that. Just keep in mind, this is the wind farm configuration that is the main framework for this work. Of course, talking about the turbine converter configuration, one could discuss different approaches, and you could start very simply with just a two-power stage solution. You just take a transformer, you add a rectifier, and you end up with a very simple solution. The problem is that the generator works with variable frequency. You're going to end up with a bulky transformer, so it doesn't seem very practical. So our approach was to use as much as possible of the state-of-the-art technology. I mean, we know how a generator looks like, we know how the active rectifier looks like, so why not just add this galvanic separated DC-DC converter on something that we already know how it works. So, as I said, keep in mind this is the subject of interest, and my highest priority was to identify the circuit, to do some loss characterization of factors, to discuss a little bit about the controller architecture. And of course, the transformer design was also very interesting, but At this point, it was with lower priority because of the time of the Ph.D. And as one would normally start when you start to investigate new technology, you first start with a survey of possible candidates. So I've spent some months and evaluated around 37 topologies. Of course, others could be identified. And I had a look at the classical bridge converter, matrix converter, MMC, dual active bridge, series resonant converter, high gain converters, and so on. And you can actually organize this family of topologies in a nice family tree and organize them from switching point of view and from galvanic point of view. But then I said, okay, there are very many interesting theoretical possibilities, but let's see what has actually been built. Let's see how can you find solution for the practical challenges. And unfortunately for DC wind farms, there's not so much practical work. But fortunately for traction and for solid-state transformers, there's a lot of work, and many demonstrators exist, many proof of concepts exist, where one could actually learn a lot from what kind of topology was used, what kind of semiconductors, issues regarding the medium frequency transformer design, how do you actually commission a megawatt setup. So for example, if we have a look in traction, we can see some very nice work also performed at ABB, and we saw very nice work from Professor Tuji. And there are so many interesting things to be learned only by reading the papers and the papers that were delivered. There are many medium frequency transformers that have been evaluated by Bombardier or Siemens, or if we look at ETH Zurich with the team of researchers from Professor Kola, they did also some very nice work. And of course, if we look at solid-state transformers, which again is just a fancy name for a power converter, we can see, as an example of General Electric, they've developed this 1 megawatt prototype employing silicon carbide modules. Or at North Carolina University and at Aachen, they also developed some very nice demonstrators. And as I said, there are many practical challenges in developing this project, so one could actually learn a lot from it. But let's remember that we are dealing with a DC wind turbine, and a wind turbine will have a different list of functionalities. And it's quite important one has to evaluate those functionalities. And let's remember we are also dealing with a different kind of environment. So one will have different design drivers for the converter. And we strongly emphasize that the main design driver should be availability, followed by electrical losses. That's quite important for this application. And also we want to employ the same controller architecture that already exists on state-of-the-art technology, meaning the generator converter is going to control the torque of the machine, while the grid-connected converter will control the input DC voltage. Talking about the modularity level, as we saw, there are many discussions and there are many philosophies discussing what kind of modularity level one should choose for this kind of application. And as is shown in traction and solid-state transformer, modularity level at converter level seems to be the preferred option from obvious reasons. It's easier to start building a smaller converter and then copy-paste it and you have series connection, parallel connection. But we are dealing with an application located at hundreds of kilometers distance from shore, tougher environment, higher humidity, salty environment, tougher specification. So we said, why not just use one monolithic transformer, which is going to be designed for kilohertz, and why not just have one rectifier? We keep the number of components low, therefore we keep the number of possible failures low, and we start simple. And as I said, we are going to design the medium frequency transformer for elevated frequency, and as you know, volume of one transformer is inverse proportional with the operating frequency. So for example, if we look at a comparison, a 50 Hz transformer rated for 10 MVA will weight around 20 tons, going at 1000 Hz, which seems to be a reasonable operating frequency, we can actually decrease the weight almost 10 times. So we could have big savings in volume of weight. So a proposed methodology was described also in my work. Now, I'm not going to go too much into detail because of time, but as I said, I started with a survey of circuits, then I had a look at survey of demonstrators in order to understand what kind of challenges one is going to get. And then, regardless of what topology one is going to select, you're going to have to perform a list of studies on that selected topology. So you have to evaluate steady state operation, dynamics, faults, and so on. Then you have to perform sensitivity studies on component level, on IGBTs, on the diodes, on the transformer. You have to evaluate the heat dissipated by all of these subsystems. You have to do electrostatic and electromagnetic studies. So there's a methodology that has to be followed. And an example of paper that was done here, it actually proposes a list of studies for these two wind farms. And for example, if we look at the different faults applied on the medium voltage network, we can see how much the output voltage can increase during the fault. And that number is quite crucial on rating the output DC-link bank. Or for example, if you have a fault of type F2, the nominal current, the short circuit current will increase to a value almost 50 times higher than the nominal current. So you actually have to design your output reactive value for that specific number. So it's quite crucial to have a clear picture of this list of studies, to evaluate the specification, and then to properly design the converter. Two other tools were employed, and as I said, I'm not going to go too much into detail now, but I've mainly used the failure mode defect analysis, and it's a really useful tool to give you an idea on the number of possible failures the system is going to experience. And then I've also used this concept selection tool entitled Q matrix, where you basically start with the current base design, baseline design, which in this case was a full bridge converter, and then I've actually compared optional concepts to that baseline, and you can get an idea if the topology is much better, worse, and so on. So basically from 37 topologies, I've down selected to 5 topologies with characteristics like single phase, unidirectionality, varying separation, monolithic transformer, and all those 5 topologies, they have common characteristics like there's going to be an inverter, there's going to be a monolithic transformer, there's going to be one rectifier. So if we start with the full bridge converter, that would be the most simple approach, right? You have a full bridge inverter, you have a medium frequency transformer, and the rectifier with series connected diodes. Here we can see the characteristic waveforms, and I've also built a loss model for the converters, a semiconductor loss model and a transformer loss model. So if we evaluate the total losses on this topology, they will range below 3% operation. We're going to have hard switching losses at turn on and at turn off. The next option would be to use a single active bridge converter, and we can see how the current is going to change from trapezoidal to triangular waveform. And basically the converter is employing the leakage inductance of a transformer, and this allows us to have 0 voltage switching at turn on, thus eliminating the turn on losses. So we can actually improve a little bit the efficiency, but the big disadvantage is that building megawatt transformers with a small leakage inductance is not so practical. So such a converter would actually require a 0.1 leakage inductance, so it's not really practical to go into it. And of course one could actually discuss why not use a dual active bridge converter. But if we consider about the requirements that we've imposed, we're going to end up with series connection of active devices, active IGBTs, and if we're going to have around 100 kilovolt on the output, turning on and off so many series connected devices is not going to be so trivial, plus the cost of the rectifier is going to increase. So the dual active bridge was no longer discussed. Then another important thing, we are talking about medium frequency transformers. When you go at high frequency, you have to consider the impact of the stray capacitance and the leakage inductance, right? Those parameters will heavily influence the secondary voltage, which will experience overvoltage and will have oscillations, and that is going to translate into tougher design specification for the rectifier. But we already know, and we already know from the 80s, resonant converters, they were a preferred option, especially for NES applications, because they could actually employ medium frequency transformers, and their non-idealities could be used in the benefit of the converter. So we said, okay, let's focus on the LLC converter. It was suggested in traction converters. And it was suggested at operation with constant frequency while being operated below the resonant point of the LC tank. And we're going to end up with a very nice quasi-sinusoidal waveform, which means 0 voltage switching at turn on, and a very low turn off current. And this is going to translate in very low losses. So seems like a very interesting candidate. But the problem is that when operated with constant frequency, and it's not going to be possible to control the LC converter. So the question was how to control a high power, medium voltage resonant converter. And there are different options. One can actually employ frequency control. One could actually use phase shift or duty cycle control. You can actually use both. And in the world of low voltage, in the world of low voltage resonant converters, they are normally used with variable frequency operation. And in our case, we said, let's start with the variable frequency series resonant converter. So we have an LC tank on the primary winding, and the converter is operated below the resonant point of the LC tank, and is going to experience this continuous conduction mode, which means we're going to have this nice sinusoidal current, which should translate in soft switching capability. And the very nice characteristic of the converter, we can actually control the output power by basically controlling the distance between the pulses. So when we change the frequency, we actually change the applied volt seconds on the transformer, right? And then we change the distance between the pulses. Average output power becomes a function of frequency. So for example, at 1000 hertz, the converter could deliver 10 megawatts. At 1 megawatt, at 100 hertz, the converter could actually deliver 1 megawatt. But variable frequency is not appreciated by the transformer, meaning we are playing with the flux linkage. And this option is actually going to end up with a bulky transformer because the transformer has to be designed for the lowest operating frequency, right? So the question is, okay, how can we actually remove this issue? And we've introduced this so-called pulse removal technique. The LC tank is moved on the secondary side. I'm not going to go into detail why it works like this. I can explain also in the thesis. But we can actually design a transformer for high frequency operation and operate it with low frequency. And the way to do it is to clamp the inverter output voltage to 0 when the current has also reached 0. And by doing this, we can actually keep constant the transformer flux linkage. And as in the previous case, at low power operation, we deliver only a few pulses, while at rated power, we increase the density of pulses. So now we have a means to control output power. We can design the transformer for medium frequency operation, and we have also soft switching capability, which is translated in low losses. If we should compare the losses of these two options, the classic SRC, which had the transformer designed for low frequency, the problem is that we're going to pay a big penalty on the losses, on the winding losses, and we can see here at around 100% of the nominal power, we're going to end up with close to 7% of losses, the vast majority which are on the windings, while with the improved SRC, entitled SRC sharp, losses can actually be kept below 1.5% of operation. So it looks quite promising, and from this reason, with these reasons, it was decided to continue with the SRC sharp as an optimal topology. And as I said, we're going to have modularity on the inverter side, and they are going to employ 6.5 kilovolt IGBTs. We will have these medium frequency transformers with high turns ratio. The resonant tank is placed on the secondary side, and I need to emphasize that it would prefer that the resonant inductor is actually incorporated as the leakage of the transformer. And also very nice characteristic, the rectifier can actually be assembled with press spec diodes, line frequency diodes. So, and the transformer, we envision a transformer with amorphous core material and foil winding. So actually we're talking about off-the-shelf technology. Now, if we look at the device waveforms, we can see that the IGBTs will experience 0 voltage switching at turn on. They will exhibit a low turn-off current, so also the switching losses have increased, while the diode will experience 0 voltage switching at turn on and 0 current switching at turn off. The converter will exhibit different modes of operation. And these modes of operation, they are actually impacted by the switching frequency and the difference of voltage between output and input. Most ideally, we would like the transformer to operate in the so-called DCM1, discontinuous conduction mode, where the relation between power and frequency is purely linear. But as the output voltage decreases, and it could even exhibit the so-called CCM1 mode of operation, which is a not wanted mode of operation. In that case, the characteristic would become non-linear, and it would be quite hard to control the converter in that operation. But that is going to occur if we have a big voltage drop on the output. And yeah, these modes of operation, they are also detailed more in the thesis. Now, discussing about the passive rectifier, as I said, we are suggesting the series connection of line frequency diodes. They are cheap, robust, they exhibit low conduction losses. Here you can see a conceptual drawing of the valve. Mineral oil encapsulation to be used for cooling and also for insulation. And also, an important thing to be addressed is the voltage sharing across the diodes during the dynamic and static transitions. Different diode parameters can actually impact that voltage sharing. And I did some studies, and for example, plus minus 5% variation in the Stokes charge could actually lead to plus minus 45% in voltage variation. And the designer has to address these things. And the way to do it is to simply add parallel RC circuits that can actually help on achieving the balanced voltage. Then we discussed what would be the maximum frequency that line frequency diodes could actually be used, and a rough number would be around 5 kilohertz, and that number comes from the time necessary for the Stokes charge to be evacuated. Talking about the controller architecture, I have a colleague from Taiwan, Yushin Chen, and also we have a few master students who have collaborated on this topic, and a controller architecture was developed. It's basically it's a basic controller structure that helps us to operate at steady state operation, and it's composed from a feed-forward controller. The feed-forward controller is designed based on the relation between power and frequency. But as I said, if the output voltage drops too much, we might exhibit high nonlinearity. And in that case, we need the help of a gain scheduling PI compensator that is actually going to help with a few percent the feed-forward controller. And for example, here we can see a few results recorded from the lab. We can see some dynamic steps. With the blue line, we see the behavior only of the feed-forward controller. Without any help, it is going to reach steady-state operation, but with a small error. While with red, we can see the behavior of the feed-forward controller plus the PI compensator that helps it to remove the error. Following, I'm going to discuss a 10 megawatt design example where I'm addressing the volume estimation and the number of components. We're talking about plus minus 2 kilovolt on the input, plus minus 50 kilovolt on the output. Possible cooling technologies could be water and glycol on the power stacks, mineral oil encapsulation on the transformer and on the rectifier, and natural air cooling on the resonant tank. For example, on the inverter, we're going to have 3 parallel power stacks with 12 devices in total, estimated losses around 0.27%, and compared to a hard switch topology, we should exhibit around 2%, so there's a big decrease in losses. Further on the rectifier, around 160 devices should be used, with total losses around 0.4%. Further on, a conceptual drawing of the medium frequency transformer, and here I've barely scratched the surface. We, as I said, we envision a simple structure based on amorphous core material, metaless, with foil windings on the primary and foil windings on the secondary. Without oil, the total mass would be around 1.2 tons, and estimated losses around 0.2%. Some evaluation of the resonant capacitor bank and also the output capacitor bank. On the resonant capacitor bank, based on the selected subunit, we should end up with around 240 devices, while on the output capacitor bank around 400. And if we should compare the estimated volume of the system with the standard shipping container, we can see that from all the subsystems, apparently the output DC would occupy the highest volume. But quite interesting, if we should compare the volume of the DC-DC converter to a 50 Hz transformer with same power level, we could actually have 6 times lower volume and size. So very nice savings in space and volume. Now, I'm going to address the medium voltage experiments which were performed in our MV lab, and it was really interesting to go through all the practical challenges. And we have a lab room where the space is divided between the control room and the power room, and the user always sits inside the control room in safety and is able to control the medium voltage setup without any issues. But of course there were many discussions related to safety, to responsibility, proper training is necessary, and medium voltage prototypes for Ph.D. students and master students are not so trivial, but it was really interesting to work on this. And of course, one has to address the testing methodology, like how many iterations are necessary to develop a megawatt setup? What is the commissioning process? How many objectives can be achieved through one experiment? During my work, there were around 4 experiments, and in the presentation I'm addressing the last 2. The first one is a proof of concept, 10 kilowatts, 500 volts to 5,000 volts. Here we can see the full bridge inverter. We have a 1 to 10 turns ratio transformer with amorphous core material employing foil windings. Then we have the rectifier with 12 diodes connected in series. All of them are line frequency diodes. I could not get Prescott diodes for this non-specification. Then we have on the secondary side a hand-winded resonant inductor and resonant capacitor. While on the output we have a medium voltage source, and in this setup actually we were able to emulate the medium voltage network. So we had this medium voltage source connected to these series connected diodes on this resistor band. So let's say in simple terms, when the converter is operating at 10% of the nominal power, the medium voltage source will cover the rest of 90% of power. So by doing this, we can actually emulate a constant medium voltage network. Here you can see some actual recorded waveforms from the laboratory, and we can see how pulse removal technique is being implemented. With blue line, we can see the output voltage close to 5,000 volts, while with the orange we can see the applied voltage on the transformer primary winding. And then we can see the primary and the secondary resonant current. And for instance, when it's operating at low frequency, as you can see here, that is actually the magnetizing current flowing through the transformer. It's kept constant, so we are not saturating the transformer. One of the main objectives of the setups, besides implementing the controller, was to evaluate losses and to do a preliminary semiconductor loss model validation. So the strategy was to use low voltage probes on the input side, high voltage probes on the output side, Then I was recording the current and voltage on one IGBT and on one diode. They were recorded with the oscilloscope and then compared with the MATLAB tool. And as we can see here, on this prototype, losses are ranging from 6% down to 4.5%. And the really nice thing is that the inverter losses and the rectifier losses, they match with the loss model. So that increases the confidence in the loss model. Of course, one could discuss why the excessive losses, and one explanation is that because the resonant inductor is hand-winded, I had a better quality factor, which translated in higher losses. Plus, the employed IGBT and diode devices, they were utilized to around 25%. So they were not the most optimal devices for this specification. But as I said again, the loss model predicts also the same values. Another objective of the setup was to evaluate the voltage sharing across the rectified diodes. And here we can see, for instance, on this branch, how blocking voltage looks like on the diodes. And one diode is always going to block faster than the others. And for example, a diode rated for 1.6 kilovolt was exhibiting around 2.5 kilovolt. So if I would have operated this for longer term, it would have led to extraction of the rectifier. But with the proper design of the RC circuit, we can actually achieve almost even voltage sharing across the diodes. And this further on builds confidence that the rectifier can be designed for higher specification. And finally, really interesting setup that took some time to develop, but again, it built confidence in the topology. So the goal here was to employ actual 6.5 kilovolt IGBTs and 6.5 kilovolt Raspberry diodes. The goal was to emulate the target waveforms, kilovolt and kiloamps, without actually using a megawatt DC source or a megawatt resistor bank, or actually delivering the power into the grid. So we had a setup where basically, you can see here the principle of operation. From this MV source, we were building voltage on the input capacitors, so we were increasing the in, while switching in the same time the converter, we were also building the output voltage, right? And at one point, we would stop the gate signals. Output voltage was discharged through some bleeding resistors. And when I had enough voltage difference between input and output, I was applying again the gate signals. And for a few milliseconds, I could actually recreate kilovolt and kiloamp waveforms. And then I could record them and compare them with the loss model. So for example, here you can see some recorded waveforms, one at 800 Hertz and the other one at 300 Hertz, voltage ranging from 4,000 volts, current reaching to close to 1.5 kiloamps, or in this case close to 2 kiloamps. And for example, here we are looking at the waveforms recorded on the IGBT. For instance, these are the recorded IGBT waveforms, and I can actually recreate the same waveforms in the simulation model. Another aspect to be mentioned is that we had this fifth IGBT in series with the primary winding, and the goal of the IGBT was actually to measure conduction losses. So we had this high voltage fiber optic isolated probe, and we could actually measure the forward voltage drop. And you can also notice this voltage spike, which my assumption is that this is due to the stray inductance of the power module. And then if we compare the conduction losses of the analytical loss model with the recorded losses, the difference is because the loss model was first developed for 120 degrees, while in the lab I was just operating at ambient room temperature. On one IGBT, I was using high voltage probe to measure the collector meter voltage, while the current was recorded with LEM current probe. If we should zoom in the turn on and turn off process. Here we can see very low losses, around 8 watts at turn on, very low losses at turn off. This should be actually 0, but because of the nature of the setup, because I'm actually sending only a few pulses, the magnetizing current through the transformer is slightly offset because it doesn't have enough time to reach steady state. But ideally, or I expect in the actual application, the turn-off losses to be close to 0. Now, looking at one diode, we could recreate we could recreate around 1.5 kiloamps, but because of the transient process, turn-on voltage was close to 1,000 volts. In order to measure the forward voltage drop, the strategy was first to charge the input capacitor to around 1,000 volts, while the output capacitor, they were not charged at all. And that actually allowed me to use a differential probe to measure the forward voltage drop. And again, here you can see the experimental waveforms compared with the simulated waveforms. The spike in voltage that we see here is the normal reverse recovery process, but then it drops to 0, and the reason is that the converter actually goes in the so-called X sub-interval mode of operation, where actually the rectifier is reverse biased. So you could actually see the rectifier totally disconnected from the output voltage source, or actual voltage capacitors. And again, you can see here, if I input the recorded current waveform in the loss model, predicted conduction losses, they are quite similar. Again, zooming in during the turn on and turn off switching intervals, at turn on losses are 0, while at reverse recovery we exhibit some quite high losses, around 4.7 kilowatts, and I'm going to explain a little bit why this happens. So here, for instance, if we input the recorded waveforms, one IGBT and one diode, right? Recorded waveforms from the lab, if we input them in the loss model, we can see how much the losses per device should be. And they are quite similar with the measured losses. And if you remember, on the 10 megawatt theoretical example, the predicted losses were around 0.27%, while for the rectifier losses, they were around 0.41%. In the lab, during one pulse, while operation at 1,000 volts, I could actually recreate burst power close to 2.8 megawatts, and at that level, inverter losses, so measured inverter losses, they are around 0.24%, while the rectifier losses, they were almost double than the predicted ones. And the explanation is that in the lab, the Prespect diodes that we could get, there were actually some avalanche diodes. They were not the target devices that we intended. And they exhibit actually 5 times higher stored charge than the target diode. So the expectation is if we can get actually the preferred diodes to see the reverse recovery losses also similar. So I can say that there's high confidence in the semiconductor loss model, while work still has to be performed on the transformer. I am reaching the conclusion part, and during my work, as I said as a summary, I have investigated a high power medium voltage resonant DC-DC converter entitled SRC Sharp. The converter was modeled and it was analyzed, and I've discussed conduction modes. I've also developed medium voltage experiments, which I believe have increased the technology readiness level. Main contributions: a new modulation scheme for a single phase series resonant converter was investigated. Circuit conduction modes have been identified. The semiconductor loss model has been validated. A novel soft-switching characterization setup was introduced. We've also evaluated the closed-loop control, and also a design guideline for the SRC Sharp has been proposed. Of course, there is also future work that has to be done, and my proposal is that a setup of around 0.2 megawatts with plus minus 10 kilovolt voltage output should be investigated, and at this level we should do transformer loss model validation to some calorimetric setup. So this concludes my presentation, and at the end I would like to thank Pierre, who has been an excellent supervisor. I appreciate all the time and energy he has spent with me, and I've learned so much from him in the last 2 years and a half. I would like to thank the co-supervisors Klaus Ledbeck and Stig Nielsen for the help with the lab, with the equipment, with the feedback on the papers and the thesis. And of course I would like to thank Professor Dražen Đužić and to Dr. Maye and to Associate Professor Nikolai Beck for putting the effort in evaluating my work, and of course for traveling so long here and to have these discussions. I would like to thank the Department of Energy Technology for all the financial support in the last years. I would like to thank all my colleagues and all my friends. And in the end, I would like to thank my family, especially my wife, Andrea, and my kids, Luca and Lara, who have supported me in the last years and shared the love. And it was a very interesting journey to be done. So thank you, everyone, and I hope we're going to have an interesting discussion.
We'll have a short break.